So principal component analysis is a linear transformation of raw data, but sometimes our data is very, very nonlinear, and in this case, so other nonlinear methods could be more helpful than principal component analysis. So tSNE is, well, one of these nonlinear transformations of data. So tSNE is a relatively new method. It was published in 2002. Well, it is fairly complicated, so I'm not going to get into deep details of this method, but I think it is a good idea to at least, well, get some familiarity with it and to know that it is out there and it is helpful. So what kind of data would tSNE be helpful for? So here is an example. So this is fashionista data set from Lab 7, right? Now, recall that in this data set, P is, well, every observation is an image, is a 28 by 28 grayscale image, right? So then if we convert it to a vector, then the number of variables is going to be 28 times 28, which is 784, I think. Right? And if we apply principal component analysis to this data set and plot just the first two principal components and color them according to the type of the image, so the accessory that is shown on the image, there are 10 types. Then we see that we do see some kind of something like clusters here. I don't know. So there is some structure here, but clearly it is still very, very messy, right? So even though we do see structure, I mean, imagine that you didn't see these colors. So without the colors, you wouldn't really be able to, I mean, without the colors, you probably would see some, like that these points are close to each other and all these points are close to each other, but you wouldn't really see that there are like 10 different types of the images. So tSNE does a much better job on this data set. So here is what tSNE produces, right? So I took the same data set, all right, and then applied tSNE to it to get to reduce the dimension from 784 to 2. Right? So I constructed a transformation of my 784 dimensional set to 2-dimensional set. And then I plotted the 2-dimensional set as a scatter plot, and I colored the plots according to the type of the label. And now we see that, you know, it's kind of, there is a nice structure here, and just looking at this, we see that even knowing just these two dimensions, we probably would be able to predict the label of an image quite well, right? I mean, not all of them. So t-shirt, if you remember, t-shirt is quite hard to predict. So t-shirt is kind of scattered around, right? But some of the types are really clustered together, which means that it would be easy, well, relatively easy to predict them using by some simple technique. Okay, so this was about motivation of tSNE algorithm. So how does it work? Well, the idea is that first, if we have data points in RP, then the first thing we are going to compute similarity between two data points. So for all pairs of I and j, right? And the trick here is that it's not simply the distance between these points, but something slightly different. So the first thing that we're going to do, we're going to compute this Pj conditioned on I. And the meaning of this is that imagine that at point I, there is some kind of a wizard that picks other points, right? And this wizard picks other data points with probability proportional to the density of the normal distribution centered at that point. So this PJI is the probability that point J is going to be picked, right? So this is some kind of probability to pick point J by a wizard stationed at point I, who picks other points with probability proportional to the density of the normal distribution. Okay, such a probably a bit strange method to define similarities between data points. So then Pij is just the symmetric version of this. It's going to be Pj conditioned on I plus Pi conditioned on J. And then we divide by 2n to make sure that the sum of all Pij over all I and J should be 1. The reason for this is just because we want to think of this Pij as a probability distribution. Okay, so then tSNE learns a t-dimensional map, right? So it is a map from Rp to Rd. Well, for visualization properties, usually d is equal to 2, but it's not restricted to that, right? So, and then it maps xi to yi. I'm not sure. So maybe yi is not a good notation, because usually we think of y as a response variable. Here, we do not have a response variable, right? So I thought that it would be okay to denote it by 1. But again, so here, there is no response variable. This is unsupervised learning. Well, and similarities between yi and yj are defined in a similar way. So only instead of Gaussian distribution, we take the student t distribution with 1 degree of freedom, right? So basically, the formula that you see is t distribution with 1 degree of freedom. With 1 degree of freedom. And this is what T in tSNE stands for. Right? So without this T, we probably would use the same formula for Qij as the one for Pij. This would be just like a pure SNE. With T, we use the T distribution here. Okay, these points yi are determined to minimize the Kalbeck-Leibler divergence between P and Q. So what is it? If you haven't learned it from other statistics courses, then you can just look it up, but the formula is just here, right? The formula is just here. So this is the Kalbeck-Leibler divergence between P and Q, and it shows the similarities between two probability distributions. And basically, we want to minimize it. So we want to make the probability distribution Q as close to probability distribution P as possible. And this is done by gradient descent, right? So we are going to find, this is a function of y1, y2, and so on up to yn, and we're going to differentiate this expression with respect to these y's, and we're going to use gradient descent to find the minimum of that expression. So this is very similar to logistic regression or to artificial neural networks. Only here, instead of the loss function, we have this Kalbeck-Leibler divergence. Okay, so one more thing is that in here you have this parameter sigma I, and sigma I is not a hyperparameter here, but there is a hyperparameter. So there is a hyperparameter that is called perplexity. And again, I don't want to spend too much time on this, so I'm not going to explain what this perplexity is, and of course it's not going to be tested, but you can just read about it. But the idea is that once you set this perplexity, then sigma I can be chosen in a way so that in regions where there is a lot of data points, here sigma I is going to be small. And in regions where data are scarce, sigma I is going to be larger. Sigma I is going to be large. And the balance between large and small is going to be chosen to match this perplexity parameter. So the tSNE algorithm has one hyperparameter. So how do we choose it? Well, basically there is no good way because there is no such thing as cross-validation here, since that there is no response variable. So we cannot really figure out why one choice could be better than other choice. Well, in an obvious manner, right? So if you really want to learn about it, you could just read research, and of course, if you read research and mention it in your report, you will get some extra scores for your report. Okay, so there are some other methods of dimension reduction that I mentioned that I would like to list here. So autoencoder is based on neural networks. Mapper is based on topological data analysis. So this is something that I am interested in because my PhD was in topology. So I think it's fun stuff. And UMAP is based on some manifold, some differential geometry. So again, this is something that you can explore in your course project, or who knows, maybe you can explore it for your final year project. So that was all about tSNE. Thank you for your attention.